Hey, Jesse, how are we doing? It is Monday morning. We got time for the test. What topics are you wondering about, Jesse? What chapters, what topics? Mary's looking all crazy today. It's fine, though. What topics, what chapters are you wondering about? Here we go. Let's see. Hey, what's up, Ethan? What's up, Grant? Man, we got a bunch of people here. Mewbot's awake in the chat. Give out 100 points. Good to see you, Brianna. Good to see everybody. What topics are people wondering about? Good morning, Sloan. Whoa, that Discord message, I think, got a bunch of people here. Awesome. What's up, Trenton? What topics are people wondering about? Name the topic. We'll start reviewing it. What topic are people wondering about? Look, we got it on the screen over here. The last two chapters, look, variance inflation, standard error inflation, R squared sub I, what? Multiple regression. Good to see you here, Hayden. Chapter 12. Well, so chapter 13 and 14 looks like first. Okay. So in a chapter, let's review chapter 13 and 14 right here. So here we go. 328, stat 201, reviewing chapter 13 and 14. Now, the first thing I want to point out right here, whenever we'll do some chapter 12, Ethan, you bet. Whenever you get a chapter 13 or 14 question, the first thing you want to do is what? The first thing you want to do is what? We mentioned this yesterday during the Kahoot. What's going to be the first thing you do? And we're going to open up tab right here. Just over here. The very first thing you want to do. Oh, no, I've had this one a while. I guess I haven't worn it in a while. Thank you there, Sloan, right there. Cat or quant, right? Cat or quant. So you've got your formula sheet, and do check out this page. There are videos going over each chapter, speed runs, going over the test practice questions, going over the chapter more in depth, a more traditional review. So this can help you out reviewing the chapters right here. If you go to probability, you will get a video right here of me reviewing all of probability in 18 minutes. So pretty good video of that. You go down here, you get a totally different view of it, an epic speed run, 24 minutes. So the speed run's longer than the full video. Where do we go to find the exam review page? And put it in the chat right there. Help Grant out. Mewbot will put it in the chat for you. Where do we go to find the exam 2 review? Help out right there. 100 points for people helping out. I know someone's going to... Will you have to calculate the line of best fit on the exam? Kind of, Olivia. I mean, we'll look at... check out the speedrun video to see all the topics you're required to do. There's some mathematics, not a ton. You could have to calculate residuals, calculate observed. No concepts like that right there. Thank you there, Sloan, helping out. Okay. So we're going to go over here to the formula sheet, which is super important. Okay, so what do you have to know when it comes to the formula sheet? You have to know your what. Like, you'll first need to know, is it cat or quant? Proportions are like, what is the proportion of people who own a dog? Well, that would be a question of, do you own a dog? So that's a categorical question. And so you have to know your what. As Leo always said, know your what here. What do we have to know on this form right here? We have to know our what. 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 Notation.
Notation, brother.
You're going to know the notation. And I do mean this if you're watching this video right now. How many of these symbols in here should you be able to tell me? How many of those symbols inside of here should you be able to tell me? I'm going to tell you what each one means here. So how many of those symbols should you be able to tell me? All of them. Jerome got it right there. Exactly. Every single one of them. So here's what each one means. Well, first off, and this is knowing your formula sheet, proportions are categorical and the mean is quantitative. Exactly. Because like the mean of GPA is a quantitative question. What's your GPA? Quantitative. And proportions are categorical, like the proportion of people from Knoxville. Are you from Knoxville? Categorical question. So when we do proportions right here, we have this quantity. And practice in the chat, what is this known as? How would you explain that quantity to someone right there? Visually, it looks like this. That's what it looks like right there. What is that quantity? Like, it is mu p hat, but what is mu p hat? That's in good answer, Sloan, right there. That's what it says. But what does that mean? What is that conceptually speaking? Like, what is the point of it? So it's the center of a distribution. Great job, Hayden, right there. It's the center of a distribution. We'll throw Hayden 100 points. So when I read it as the expected sample proportion. The expected, well, it's not the true proportion yet. It's equal to the true proportion, but the expected sample proportion. Does that make sense? That if you took a sample proportion, you would expect to see this. So this is when, and Sloan mentioned that this is the true proportion or is equal to that. So if UT tells you that 20% of students are from Knoxville, what does this quantity mean down here? If UT tells you, and that's the true proportion, they say, oh, 20% of students here are from Knoxville. What does the quantity then mean when we bring it to a sampling distribution? Like, what does it then conceptually mean down there? Like as a full sentence, like, oh, UT says the true proportion, like 20% of students here at UT are from Knoxville. That's the true proportion. UT's telling you it. Like we have the data. We know 20% of students are from Knoxville, and that's what P is. It's the true proportion. So what does that quantity mean down there then when you bring it to the sampling distribution? So remember I said expected sample proportion. So what does that mean? And basically, Jesse, right there, if you took a sample, you would expect to see 20% in your sample. Does that make sense? That's why it's expected sample proportion. So not quite, but on average, you would see that in a sample. Like over repeated trials of taking samples of students, you would see on average 20%. It is kind of average, and I know mu means true mean by itself. That's where usually confusion arises. This is not a concept you multiply together. It's one phrase, like the expected sample proportion or the mean of the sampling distribution. But I like to say expected, and then I think it makes more sense to say, if I took a sample of students, I would what? If I took a sample of students, this is the truth. If I took a sample of students, I would what? If I took a sample of students, I would what? The most likely thing, what? If I took a sample of students, I would what? If I took a sample of students, I would what? I would expect in my sample what? So this is the sampling distribution. I think what is the hardest thing for people to realize is theoretical. It's saying, well, I know 20% of students are from Knoxville. So if I took a sample, then if I took a sample, I would expect 20%. Yeah, I'd expect 20% of my sample to be from Knoxville. Yeah, to be whatever the conforming thing is. If I took a sample of students, I would expect to see 20% of students from exactly, Brianna. Great job right there. Now, are you always going to see that? Like if you take a p hat, is every p hat going to be right here at the center? So this is every time you and your friends go out and take samples. Every time you take a sample, is it going to be right there at the center? Is it? No. There's going to be what? It's not going to be like, it's not going to be 20%, 20%, 20%, 20%, 20%. Sometimes 20% is not even theoretically possible. Like if you were to talk to 101 students and you had that X is this, what is P hat currently equal to? This is more notation you should know right here. What is P hat currently equal to, which is the sample proportion? So what is going to, it's going to be very close to that. Be careful, like keep your decimals on this. But P hat is X over N, where there were 20 students from Knoxville from a sample size of 101. So there we go. Brianna has it right there. So it's not exactly. And you'd want to know if this is odd by doing P hat minus P over the standard deviation of P hat. This would give it context right here, and you see that over there on the side where we're doing a z-score for the p hat we observed. So that is the very far thing, and we need the standard deviation, because the standard deviation, which is just this formula right here, is going to tell us the spread of the distribution, and we could go out 3 standard deviations right there. So we need to know that there is variation noted by the standard deviation. So how in the world are we going to get Q? Now, I think a lot of people understand this by now. But how in the world do we get Q from this? So we have this information. We would need Q right here. How are we going to get Q? Very quick, very easy. If you know P, what's Q? Same with P hat and Q hat. We won't use Q hat for this. It'll come up in the next chapter. Exactly, Brianna right there said it perfectly. It's just the complement. Also reviewing a little chapter 12 right there. So to find the standard deviation, you just plug into the formula, and we have 101. So that's going to be the standard deviation of the distribution. It's probably about 3% or so. You can change it to percentages afterwards. These are decimals, and it's P times Q over N square root, 4%. So it's basically 4%. So 3, 9. Oh, forgot a 0. So if somebody saw in their sample 34 students, would this be odd? First off, calculate what right here. First off, 34 out of their 101 students. Oh, a space right there, Sloan. Space between will do it. First off, calculate what from they saw 34 students out of 101. So calculate what right there. What do you need to calculate right there? What should you calculate right there? What should you calculate? So 34 students out of their 101 students were from Knoxville. So then you have to think about, what do I have? I have 34 out of 101, p hat. So we need to go x over n equals p hat. P hat is going to be about 0.338 or so. Is that correct? It's going to be right under 34%. So x over n, about 338. I'm just estimating right there. I guess I could always put it into the calculator. I would suggest doing that on the test. And it's 337. So very close. Okay. So now that we have p hat calculated, we have to ask how odd p hat is. Now I want you to look at the top of this equation. The top of the equation is just a what right here? The top of this equation is just a what right here between two whats? The top of the equation is just a what? The top of that equation is just a what? Not it's not quite a residual. Residual is observed actual minus residual equals actual minus predicted or observed minus predicted, but not quite a residual. It's similar in concept, Jerome. Counterpoints right there. It's just, think of a D word. It's just a what between two numbers. This is the way all z-scores work. It's just a what? A difference, and then we divide it by standard deviations. And think about this. We're standardizing the difference, and that's what a z-score is. Does that make sense? We're taking a difference. When we first learned it, it was observation minus mean over standard deviation. And if you look at the similarities in all these formulas, the top part is just a difference, and then the bottom part is just a standard deviation. So when you realize z-scores are just differences, there's the difference for all of these formulas, and then all you're doing is dividing by a standard deviation. Every time you get a z-score, you're just standardizing a difference. Like, how far is the sample mean away from the mean of the distribution? How far is the sample proportion away from the mean of the distribution? So we have to think about, like, why we're doing this. We're giving it context. So what is the z-score here? What is the z-score? And I purposely use numbers that I can kind of estimate the answer to. So go ahead and solve the z-score. We've got all the notation right there. What is the z-score? The z-score is what? What is the z-score? Great job, Janie, right there. 100 points, following along. The z-score is what? Go ahead and plug it into the calculator. Good practice right here to make sure you do them correctly. What is the z-score? Yeah, I was thinking about 3.3 or so. Great job, Brianna, right there. So is that weird? And I do like to do z-scores like that. I don't like a difference of like 2, because 2 is like iffy. Oops, you see, we should think about what it is. And I did it wrong, because when I put it in, I was like, that was not the answer I was expecting to get. There we go, that's what I was expecting to get. Always think about what you should get when you put it into the calculator. 3.44, am I doing it correctly? Let me double check. Or I think it was 0.3366. I think it was that. And so I think people have carried more decimals. If you feel like a rounding issue got you on the test, just let us know. And there it is right there, 3.342. That is the answer people are getting. 3.432. And there we go. Is that weird? Is that weird? We actually landed way over here, or that's our third scenario, 1, 2, 3. We landed even further over here. So we landed about there at a z equal to 3.432. And so that's pretty far off the curve. Having an issue of 0.337 is very unusual because we calculate the z-score. We know the z-score. Yeah, Brianna. Wow, amazing justifications. Brianna perfectly says it there that z-scores outside of -3 and 3 are pretty unusual, or very unusual, we could say. Outside of -2 and 2 is kind of unusual. It's not like 1.99 is usual and, you know, like 2.0 is very odd. Z-scores are the further you are away, the more odd it is. So think about it as shades of gray. Like within here, it's kind of odd. And then within here, it's pretty normal. Like within... So after 2, yeah. So within here, it's pretty normal. So that's pretty normal within here. Like within -2 and 2 is pretty normal. And then this is kind of odd. And then this is really odd over here. Does everyone understand, conceptually speaking? I think this is one of the hardest things for people to understand. We'll just make this all z-scores now. I think one of the hardest things for people to understand about statistics is it's not about certainty. It's not like something instantaneously becomes odd. The wider the z-score in terms of absolute value, the more odd it is. So notice how within -2 and 2, it's like, yeah, that's pretty common. In between 2 and 3, in terms of absolute value, is kind of odd. And then outside of 3 and +3, -3 and +3 is very odd. So, you know, 2.99 is pretty odd. It's basically 3. 2.9 is pretty odd. It's kind of 3. 2.5 is, it's odd. It's between 2 and 3. 2.1 is a little odd. But once you reach 3, no statistician is going to tell you outside of 3 and -3 is not odd. That's very unusual. But we do reach like these gray zones. It's not like 1.99 isn't kind of large. Does everyone understand that? I think that's the complexity. Where did you get the 0.8 from? So where do we get 0.8 from? How did we get 0.8 right here in this equation? So we're looking for p times q over n square root. P times q over n square root. Help out right there with 100 points. How did we get 0.8 right there? 1 minus p, exactly. It's a compliment. Great work. Thank you for everyone helping out right there. Good questions. Another 100 points for asking those questions. This was basically understanding how to work this and what are the 3 conditions we would have to pass to do this. And then did we pass them? What were the 3 conditions? Remember when we do the 3 conditions, we go, the first 2, we just instantaneously say, and we pause before the third one. So what were the 3 conditions? We basically did an example problem right here. Let me mark this as chapter 13. But this was a review of chapter 13. And then we'll do chapter 14 next. So let me put right here, chapter 14. We'll do a chapter 14 problem next. And then we'll do some chapter 12. What conditions do we have to assume? Good practice right here. Know your 3 conditions. If you don't know them right now, write them down. The first 2 are going to be the instantaneously, random, 10%, and then we usually pause. Sloan did it correctly, though. 100 points Sloan. It is success failure for this. How do you know if the third condition is success failure or large enough n? How do you know? A lot of people get confused. They're like, when is it success failure? When is it large enough n? And I put some notes up here to help out. How do you know the third condition is either success failure, which states we need at least 10 successes, at least 10 failures, and we do pass that because we're expected to have about 20 successes and 80 failures. 101, I did that to be weird. And large enough n is for quantitative, exactly. So this was proportions right here. So since we were doing categorical data and this was the notation we were using, we never actually ended up using any of the quantitative stuff. We wouldn't because it's a totally different question to do that. So we did the success failure condition, which states we need at least 10 successes, at least 10 failures. Who can show me the mathematics for NP real quick? So all you have to do is find, to check success failure, you literally do NP is greater than or equal to 10 and NQ is greater than or equal to 10. So I might need this again. And so you need to find these. You need to find N, you need to find Q, and P. There we go. And so there's the mathematics right there. There's the numbers we need. Great job right there. Cassie's got it. And that's greater than or equal to 10. And then the other one's going to be 80.8, right? The other's going to be 80.8. I think so. Because they'll add up to n when you add them up totally. Great job. Oh, 82. I carried an extra decimal right there. Thank you so much. Here, wait. Something's a little bit odd because they should add up to 101. There's that one. And then 0.80 times 1. There's 80.8. No worries, no worries. No worries, Cassidy. Because a good quick check is... So what did I say is the quick check right here? Both these numbers should add up to what? Because you're saying 20% of n and 80% of n. So you're doing 100% of n if you add them up. So if you add up those two numbers, they should add up to n total. Because you're saying 20% of the sample should be this, 80% of the sample should be this. And here we'll put the numbers in. 20% of 101 and 80% of 101. And that's just the mathematics right there. So understanding like why you're doing this and what it means. And I guess I'll show the why. I do like, no worries. Oh, that's cool. New wireless keyboard. Congrats. I do like showing the why behind this. Why do we care about these conditions? You might say, why should we? What is important about meeting the conditions for us right here? Why do we want to meet the conditions? Like, why is it important we have at least 10 successes and at least 10 failures? And this shows the answer right here. Why is it important we have at least 10 successes? And look right here, we see the normal curve. It's a little bit different. This is the binomial curve, very similar to what we're doing, still shows the concepts. Now watch this. If we go down to only having one success, the curve is right skewed. So you could put this to a lower amount. Here we would only have 2 expected successes, and it's not going to be normal. And that's what Brianna said perfectly right there. To meet the conditions means the curve is normal. Or if you meet the conditions, we can use the normal curve to model the data, the sampling distribution. And so if we don't, it won't follow the normal curve. So if you notice right here, as you start to increase your number of successes, notice here we're getting 5 successes, 6, 7, 8, 9, and 10. I do want you to note this is because I'm using a sample size of 100. If I go to 200, there's now 20 expected successes, which is just n times p. And you can see right here, as we increase the successes, it becomes more normal. And about 10 successes is pretty much normal enough for us to do. Great job, Ty, right there. You can actually get a perfectly symmetric distribution at 50-50. That's as normal could be. We can calculate a lot of these quantities right here. This is done not as decimals, but I do like it that it shows the concept for us of as you increase the amount of expected successes and failures to at least 10, that we will have the normal curve. Now, why do we not meet the normal curve here? Because there's 198 expected successes. Why is this not normal? We have more than 10 successes. This is just a review of success, failure, and then we're going to do quantitative next. Why is it not normal? That looks left skewed to me. So why is the curve not normal? We have more than 10 successes. Isn't big enough. So, but think about this. We have 198 expected successes. So go ahead and quickly think about the other thing right here. Why do we not meet the success failure condition? Why do we not meet the success failure condition? Because we have 10 successes, not enough failures. Because how many failures would there be for this? And you can calculate the amount of failures. If there's 198 expected successes, there would be how many expected failures? Because remember what we said about the sample size and this. Yep, Cassie got it right there. There'd be 2 failures. You could also calculate Q right here. Q is just going to be this and just times that by 200. And now you can see there's 2 failures. So we don't have at least 10 successes, at least 10 failures. And because of that, the curve is not normally distributed. So really good work right there. Understand those conditions. Don't just memorize them. Know why we meet them. Know how to check them. Know the math. And as we did not sample more than 10% of UT students. If we're talking to UT students, 101 is less than 10% of the total population. Okay. So now we got chapter 14. We'll do chapter 12 after this. Please ask more questions, but let's review chapter 14 right here. Almost guessed the time correctly. And with chapter 14, we're doing sort of the same things, but what kind of question could I go out and ask UT students? So we'd have to write something like this. Brian, that's how I always saw Brian. Brian, what? Oh, it turned off my caps lock for me. Brian goes out and talks to UT students and asks them, what should we ask them? So we need to ask a question that's going to be chapter 14 related. And then we need to review the notation for this. So last time we were asking them, are you from Knoxville? It has to be a quantitative question. Yep. So what's going to be a quantitative question? I've used one. Don't use the one I use all the time because we've used it all the time. But what should we ask them? You name it. We do their GPA all the time because that's quantitative. Sloan's right for 100 points. GPA is quantitative, but let's do a different one. So think of a different one. What other thing could we ask them? What other thing? How many hours did you study for the test? Great job, Brianna, right there. Yep. Ask them, how many hours, dude? How many hours? Terry claims that the true mean of study time from empirical research is 10 hours with a standard deviation of 3, or let's say 7, and it's heavily right, or very right skewed. Brian talks to 144 students. Yeah, that'd be good. And finds a mean of 12 in his sample. Is this odd? Supply numeric justification for your answer. Okay. First thing, now be careful. Be careful. Is there a reason you can't hear? Your volume might be down, Mackenzie. Yep, Sloan right there. Thank you so much. Check if muted. Yeah, you might be muted right now. Yep, thank you, Sloan, right there, because I think everyone else can hear. So thank you, Mackenzie, for asking. So first things first, what do we do with this question before we start doing anything? Which we've already mentioned this a few times. What do you need to do with this question? What do you need to do? First things first. We've kind of already done it, but let's just make sure people know our steps. Determine which path to take, right? Because you've got your notes right here. Cassie's right. And we're going out and asking students, how many hours did you study? So now the best way to check if this is cat or quant is going to be ask yourself the question and answer the question yourself. So just ask yourself, how many hours did I study? You don't have to be honest, but how would you answer that? Like, think about just answering the question, how many hours did you study? Which is going to help us out right here. It's going to help us out a lot because a lot of times questions mention means. You could say the last question could have talked about the mean of the distribution because both of these can use the word mean. So we better be careful. If it says the word mean, that might not mean we're talking about the mean. But the question was, how many hours did you study? That was the question that was asked of students. So how would you answer that? I think Cassie sees it right there. Like you'd have to say something like 12. Like if someone says, how many hours did you study for the test? The answer is going to be a quantitative answer like 12, 14, 3, 1, 2, 0, whatever. But it has to be quantitative. And that means we're dealing with the mean. So be careful because you will sometimes see it talk about means and standard deviations, but that doesn't mean its proportions or means. Like that doesn't tell you enough. You have to think about the question asked. And the last one we just did a moment ago was, are you from Knoxville? And this one is, how many hours did you study for the test? Are you from Knoxville would be answered with a categorical response. And how many hours did you study would be a quantitative response. Like, are you from Knoxville? I'm actually not. Love Knoxville though. And so no. How many hours did you study? 12 hours. Now that we know this, we need to immediately start doing what here? We need to, now that we know it's means, we need to immediately start doing what here? We need to immediately start doing what? What should we do? You know what to do here. So what do we do right here?
Notation, brother.
Label that notation. What if I told you I already know the answer to this question? I will throw 500 points if anyone already knows the answer to the question of, is this odd, and provide the numeric justification. If you give me a very specific number to be like, yes or no, this is odd, then I will give you 500 points. You have to give me a very specific number that would supply the numeric justification for yes or no, this is odd. I'll give 200 points for a guess. This is I'm giving like an advanced level thing right here. If you could work through this super quick and already know all the notation and solve this out, you'd have the answer like that. But does anyone know it? 200 points for a guess, 500 points for a right answer on the line right here. We'll take the first guess. But does anyone have a guess or an answer on, is this odd with the numeric justification? If you say a certain number, I'll know you know the answer. And then you just say yes or no, and then you'd say this number, and I'd be like, okay, you know the answer. The z-score is not, is it 3.43? I'm gonna double, Brianna, you might be right. Okay, I need to check the work. Unless I've done this wrong. Oh, Brianna, I think is right. Dang it. I don't know my perfect squares anymore. Brianna is right. We're gonna change this. Okay, so here's a more fun version. Brian doesn't know. That's 12 times 12. What am I thinking? That was 12 times 12. I was thinking perfect square. Didn't know 14 perfect square off the top of my head. Okay, so now the problem's a little bit easier / funner. Let me throw 500 points for Brian being wrong when I was doing it in my head because I didn't know the perfect square. So 1,000 points were just given out. Hashtag show up to office hours, tons of points. And great job, Brianna and Cassidy, for not falling into the trap that I laid, because the thing is, a lot of people will not use the standard deviation, the new one right here. Okay, so let's check this out. You ready? With this, the first thing we need to do is mark the notation. So research shows it's 10 hours. We are assuming this is the what. Now use 2 words for this. We are assuming, well, I've already put it in there. Research shows that it is 10 hours. That's stated as a fact. So if we state something is the mean as a fact, then we're saying this is the what. The true mean. Yep, we're saying this is the truth. And then we are saying this is the what. So use the words right there. So if this is the true mean, then that is the true what. Well, that's not the sample mean right there. That would, that's not sample mean. That would be, no worries. 100 points cast, and Mackenzie. Great job right there, Mackenzie. So true standard deviation. Yeah, that's the true standard deviation. A sigma right there. Ooh, the perfect sigma. True standard deviation. Yep. And so it's the truth. Now be careful. There is S, which is sample standard deviation. We could have gotten a sample standard deviation from our sample of 196, and this would always come from a sample size right here, which 196 is the sample size. This question doesn't require that information, so I didn't give it. Questions could give you extra information, but mark your notation. So this is the sample size. So very clearly, be careful. That is the what. That is the sample size, and it gives us the mean. So be very specific. That is the what. Yeah, 2 words. That is the sample size, N. So that gives us the what. And we basically have it there if you connect the words up top. That is the sample size, so that gives us the sample mean. Great job, Cassidy. And that's how to know your notation, is to be like, okay, very specifically. If you notice, we've done a lot of the notation down here. Frankly, I think we have all of it. And now the problem is we get people saying, well, what is P? What is Q? And what's the answer for when people say, well, what is P? What is Q? They say, wait, what is P? What is Q? I can't find the standard deviation because I do not know P and Q. So what do we say? I've had people get A's on the test and ask that question. They say, I can't find it because I don't have P and Q. So this is a very common thing. But P and Q are for categorical. We're not doing that kind of question right now. That's a different sampling distribution. We went down the quantitative route. So you're doing a question that doesn't use that information. Great job, Brianna, right there. I've had people make A's on the test and ask me that question. So I understand if you make a C or a D, you're probably wondering that too. Like, it's the first thing you learn in this. So you're usually like, wait, I need to find P and Q. Okay, so when we do this right here, what does this quantity mean? Remember how we said for the other one? What does this quantity mean? It's the what if you took a what. It's the what if you took a what. So think about what that quantity means. Now, remember, I don't say true mean right there. I know that's true mean, but I say it's the what if you took a what. So if I were to take samples, these are all sample means. This quantity right here is what I would get on average. So I like to call it the what sample mean. It's kind of what I would what. So I might give away the answer in a moment. But these are good things to practice and understand. Like, if I went out and talked to students, I would expect to see 10 hours. So that's the expected sample mean. It's not saying I will see that. It's just kind of what I expect to see. Because if the truth is 10, well, then I would expect to see that, right? But not proportions to this, though. Good answer is Mackenzie right there. Remember, this is quantitative, so we won't use words like proportions right now because this is all quantitative. So this is the expected sample mean. Expected sample mean. So on average, we would see this in repeated trials of taking samples. So that's the expected sample mean. And the expected sample mean is equal to the true mean because we should probably see the truth. And the true mean right here, so we could just say mu y bar, it just equals mu. So we should probably see around what? 10. Because mu y bar equals mu, which is 10. We already know what mu is. Mu is 10. It's marked up there. Good to go. Now we need to find, because we won't always see 10. We won't be right here every time. We need a what for this distribution because we won't always land at 10, 10, 10, 10, 10. It'd be weird if we just kept seeing, every time we talk to students, on average, they study 10 hours. We won't always see 10. We need what? What do we need for the distribution? What do we need? We need a what? So it won't always be 10 every time because we said it was right skewed. It's going to load. We need a standard deviation. The standard deviation to show the spread exactly. So we said it was a right skewed distribution, heavily right skewed, and we were taking a large sample like 200. So you have to imagine for a moment that we're taking 200 people, and from those 200 people, we would get the what of the 200. From the 200 or 196, we would get the what of the 200. Now, I know this doesn't say 196 or 200, but just pretend we took 196 random people, and we'd get the what of those 196. What would we get of the 196 people? So we'd take 196 random people, condition 1 random. We'd get the mean, exactly. So every blue dot right here is a sample mean, and that's what I'm drawing right here when I show you these y bars. Every y bar here is a blue dot, and if we repeat this process over and over again, it'll actually build a curve, and the curve will be two things, more this, and that's what the central limit theorem tells us. The curve down here of the sampling distribution will be more this and more this. Two things, more blanker and more blanker. It'll be more normal and with a smaller standard deviation. And what stays the same between the two curves? Between the two curves, what does not change? So the curve, and you can see it in the notation, but you can see it here theoretically, and a lot of the MyPearson problems had you do this, the mean stays the same. And that's the concept right here, that the mean is going to be equal, or the mean of the sampling distribution, which is the expected sample mean, is equal to the true mean. The mean stays the same, but the shape becomes more normal, and the standard deviation gets smaller by a square root of n. So I wanted to use perfect squares, and I changed the question a little bit, so that when we put in sigma over square root of n, we go right here, and we get the original standard deviation was 7 over square root of 196 is equal to 7 over 14 is equal to 1/2. And so think about this. What is the z-score going to be? You can just look at this now. What is the z-score going to be for 12? You can look at it and also solve it. So this one, I wanted it to work this way. You're like, oh, well, I can kind of see it that the sample mean we observed versus what we would have expected over the standard deviation. So we take this, subtract right there, it's a difference of 2. And the z-score is very clearly what? Z-score is very clear. That's where I wanted to go with it and use the perfect square. And so great job people correcting me because I did a perfect square wrong. It's 4, yep. So that's what I was planning on doing right there with the perfect square. I was like, what's the perfect square of 14? I did 12 instead. So yep, perfect squares are nice when you just make it that way. So 7 divided by 14 is the new standard deviation. So put it this way. Would it be weird? Now be careful. I'm going to switch this question. Would it be weird if one student studied 12 hours? Would it be weird if one student studied 12 hours? Would it be weird if one student studied 12 hours? No. One student would be observation minus mean over standard deviation. So one student, 14 or 12. 12 minus 10 over 14. That is one student, which is going to be a z-score of 1/7, 0.1428. So one student studying 12 hours is not odd. What is odd? Tell me what is odd right here. What is odd is the what of what students being 12 hours. This is the big, if you understand this and can say this sentence, it's not weird for one student to study 12 hours. It's weird to see the what of what students being 12 hours. This is what's weird. And this is the sampling distribution of the sample mean. What is weird over there? Why is that weird, and what does that mean? It's weird to see the what of what being 12. So it's not weird to see one student studying 12 hours. There's the z-score of one student. It's weird to see the what of what being 12. Close, Cassie. It's weird to see a sample mean of 12 for 100 students. So remember, this is now a new standard deviation for 100 students. So that's the context we're kind of standardizing by, is the variation within 100 students. It would be weird. So you can kind of see it over here visually. Like, imagine this is where 12 hours is at. This is not the exact same distributions we have, but you would think right here something, because we landed at z-score about 4, so that'd be over here-ish. But look where that is up here. Is this really odd over here? Like, how odd is this? Super odd, kind of odd, or just a little high? On the top distribution for one student, n of 1, and we're pretending this is the n of 196, just pretending down there. Does that make sense? Like, up here, this is not odd. That is not really odd. I mean, it's high, but that's not odd. Does that make sense right there, Cassidy? Up top with the n of 1, that's not odd. But down here, where the z we calculated equal to 4, this is very odd. That's off the curve. So for the mean of 196 students, that's very odd. But for a singular student studying 12 hours, that isn't that odd. So imagine here, we'll do one more problem with this, because I think this might make more sense. You ever throw a pizza party? What might you be concerned about if you throw a pizza party and you want to order pizza? Brian wants to order pizza slices for slices for a pizza party. He knows from research that the average student eats having a pizza, right? So we want to know the average student eats 2 slices, or we could even say 2.5 slices with a standard deviation of, let's go here, 2 slices. The distribution is heavily skewed, or let's say very skewed. Brian is inviting 100 students to the pizza party. If Brian wants to be somewhat certain and order 2.5 standard deviations above the mean, how many pizza slices should he order? Okay, so I want to make a somewhat complex problem right here. So this is, I had a hard time with number 5 with the purchase exam. Yeah, we can do that. Definitely, Cassie. We'll review it. And we got the videos too, but we do an extra review of them here too. So what do you notice right here we get with this problem? This is maybe a more advanced version of this. And so let's see what we have right here. So what do we have? What do we have? We have how many pizza slices are people going to eat? So this is quant. Then what do we have next? What do we have? It's quantitative, which means we're dealing with mean. So that's the first thing we would identify when working on one of these problems. So then what do we have right here next? I'm going to mark example 2. What do we have? Let's see. That's not mu though. Good. And so this right here, 2.5 standard deviations above the mean sounds like a what? 2.5 standard deviations above the mean sounds like a what? This is a tougher question. I kind of gave you harder to identify stuff. That's a Z. Great job, Mackenzie, right there. That's a Z-score. When you say 2.5 standard deviations above the mean, that's a z-score. So we could use that down here later in the problem. So we can use it a little bit easier than working it through this formula, but 2.5 standard deviations above the mean is a z-score. So what else do we have? What else do we have right here? Oh, 2.5. Oh, good. Oh, Mackenzie, 100 points again. Are we going to throw you bigger points? Throw you 200 points. Mackenzie, you were right. I used 2.5 twice. Maybe I shouldn't do that for this problem. Mackenzie, you were correct. I was looking at the end. And there we go. And we're only missing one thing. Thank you, Mackenzie, right there. Yeah, I did it to myself too. So what else do we have right here? Well, so let's change this. Let's change this to 3 just to make it easier. Now the numbers are not the same. So I don't like using same numbers because that does cause confusion. So we've changed it to 3 slices, and sigma is 2, which is the true standard deviation. And then last but not least, we have what? Yeah, I think that helps right there, Nick. Using the same numbers can create a lot of confusion. That's N. Great job right there, Derek. There we go. Okay, so now think about this. If I invite 100 students, I would what the students to what? If I invite 100 students, I would what? How does this read? I would what? If I invite 100 students, I'd expect my what of students to do what? So what does that concept mean right there? If I invite 100 students, I would what my sample of students to do what? Yeah, I'd expect on average that they eat 3 slices from the 100 students I invited. Does that make sense? I'd expect on average, so this is expect right here. When we say mu in this case, it's better read as expected. I'd expect this. Now, is it always going to be 3 slices? Like every time I invite 100 students, is it always going to be 3 slices? Like every sample mean will be right there. Like every time I invite 100 students every semester, we have a big party every semester, 100 students come. Every time it's exactly 3 slices from that sample of 100 students. Because we just plugged in mu right there. If you're wondering how we got this, we literally just plug in mu to find that value. So is it always going to be, wow, every semester I invite 100 students and it's literally 3 every time on average? No, we need variation in it, right? So the variation right here is going to be the original standard deviation over the square root of n, which is going to be 2 over square root of 100. Now notice right here, this is nice because the new standard deviation for 100 students will be what? The new standard deviations for 100 students would be what? The new standard deviation will be what? For 100 students, the new standard deviation. Great job, Jesse, right there, reaching skydiving with Jesse level. Woohoo! It'll be 0.2. Would it be weird for 100 students to eat 5 slices, yes or no? Really quick, on average. Would it be weird? I want you to look at those numbers up there, and I'm trying to trick you. Would it be weird for 100 students to eat 5 slices? If you answer this question correctly and can explain it with the trick I'm trying to throw here, then you'll get it correct. Would it be weird for 100 students to eat on average 5 slices? Would that be weird? Would it be weird for 100 students to eat on average 5 slices? For 100 students to eat 5 slices on average. Would that be weird? For 100 students to eat 5 slices on average. And you can use this number down here. You should probably. Would it be weird for 100 students to eat 5 slices on average? Think about if you ever ordered pizza for people, would it be weird for 100 students to eat 5 slices on average? Just think about, man, I ordered pizza and everyone was eating 5 slices. That's a lot of pizza, right? I don't even know if I could eat 5 slices these days. It's more than half a pizza. Well, I would use 2 or 3, Derek. The justification we generally use. So, Rachel, we might have tricked you right there. And so think about the z-score for that. What is the z-score for a sample mean of 5 slices from the students? I've gone to a different question here for the moment. For 5 students, the z-score would be what? For 5 students, or for students eating 5 slices, the z-score would be what? A sample mean of 5 from 100 students would be what? Like if on average the students ate 5 slices, then that would be a z-score of what? So you can run through the formula over here. And so what would we get? Oops, I almost forgot that. Double check the math, Rachel. Double check the math. It's 10. Yep, Olivia's got it right there. So 5 minus 3. So let me ask you this. Is it weird, and hopefully this is where the concepts start coming together, is it weird for one student to eat 5 slices? I want you to think about one student over here. This is an n of 1. This is the n of 100 because we're using it for this sample size. Is it weird for one student to eat 5 slices? Like if one student ate 5 slices, would you be like, what? Is it weird for one student to eat 5 slices? Standard deviation originally is 2. No, because that's just a z-score of what? That's a z-score of what? One student eating 5 slices is a z-score of what? Is a z-score of 1. So, frankly, it would only get kind of weird if a student ate a full pizza. Like, you'd have to eat 7 or more slices to get to that kind of weird zone we talked about where your z-score greater than 2. Because all I'm doing is just saying 3 plus 2 plus 2 to get to 7 slices, going up 2 standard deviations from the mean. And have you ever gone to a pizza party and someone eats like 6 or 7 slices? I mean, like, that's kind of high. But once they eat a whole pizza, you're like, you ate a whole pizza? That's kind of a lot. If they eat like 1.5 pizzas, you're like, what? You're a pretty big outlier at that point. Of course, it's not normally distributed. It is right skewed. We mentioned right there it's heavily skewed or very skewed. More on that in a moment. But here's the thing. If at our pizza party, the average amount of pizza was 5 slices, which is what this is getting at down here, this would be very, very what? If the average was 10 slices at our pizza party, for the average person, like the average person is eating 5 slices, not just one person, but on average for 100 people, the average amount of pizza eaten was 5 slices. That would be very, 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 very what? And this is the average for 100 people. It's not just one person eating 5 slices. That'd be super duper odd. So we'd be like, what? I mean, we didn't really expect. And it goes back to the concept we were showing earlier, where here's the right skewed distribution of pizza slices eaten, where, you know, a lot of people are going to eat somewhere between, like, you know, some people come to our pizza party and they don't eat any. And then I'm going to mark this 32 out right here. But maybe we should go 1 here, 2, 3, 4, 5, 6, 7, 8. We'll pretend that I put the mean in the right spot. But right here is about where we landed, a z-score of 5 down here, or 10. Ooh, so we're even further over. Z-score of 10 is all the way over here-ish. So a z-score of 10 on the lower distribution, the distribution of means of sample size 100, is going to be super odd. But up here, this is only a z-score of 1. Visually, I hope this kind of makes sense. So you're changing the number of pizza slices eaten by changing... well, y bar, in the other equation, it's not y bar, though. In this equation, over on the other side, it's the observed minus the mean over the standard deviation. So that's chapter 5 right there. The observation minus mean over standard deviation equals z-score. And then the bar over here is super important that we're doing the mean. You could technically think that as a mean because it's the mean of 1, which would still just be the average for one person, which is just one observation. But that's observation minus mean over standard deviation. But this time on chapter 14, we're doing it to the mean. So the mean needs the sample size. Technically speaking, and this is very technical, why would this not change the equation? I wouldn't do this, but why would this not change the equation over here? Why would this not change the mathematics? So really good question, Mackenzie, right there. Why would that not change the mathematics down there? Think conceptually and be like, well, it's not going to really change it because why? So the number of pieces actually changes the... well, this is saying, would it be odd to see n equals 1 right there? Kristen got it. Because n is 1. So if you plug 1 right there, it's not going to change the equation. Exactly. So with this right here, is it odd to see people eating 5 pizza slices? And yes, that would be odd. It's a z-score of 10. But I drew all this out because our original question was, how many pizza slices should Brian order if he's looking for a z-score of 2.5? Where is a z-score of 2.5? Where is, I just want you to think conceptually, where is a z-score of 2.5? So think about it conceptually, and you can kind of see it. Where is the z-score of 2.5? Where would a z-score of 2.5 be? Great job, Mackenzie, right there. Mm-hmm. And think about Brianna right there. It's between 3.4 and 3.6. So it's literally right between it right here at 3.5. And we could mark the z-scores right here, and we could see that the z-score is right there. So I would need to order enough that the average for people is 3.5. So how many pizza slices should I order for 100 people? If I want to order enough that the average person could eat 3.5 from 100 people, so we're saying right here, Brian is going to order on average enough for 3.5. So that's what I'm going to order. This is now a totally different problem, the original one. So if that's how much I need to order for the average person, and we have 100 people, then what should we order? $350 slices. Mm-hmm. And you can check your work right here by saying the sum of the observations of y over n. And so they would be, we need to order a total of 350 slices over that equals y bar. And so this would be the amount right here. The total amount of pizza ordered is 350 slices. And then just kind of think about it conceptually. If I order 350 slices for 100 people, then on average, people could eat 3.5 slices. Yep. And so that was kind of a more advanced version of this problem right here. Gave some trickier stuff to figure out. And then we did a kind of side problem between there. But if you need to know the notation for these, you have to be able to like identify it. I think I have a meeting at 1:30 your time. Awesome. Cool. Got a lot of messages going on. Is there a way to watch it? Yep. It's recorded live on YouTube. Check it out. All the videos are recorded and posted to the YouTube channel. I think Cassie had a question. Cassie, do you want to mention your question again real quick? It was which one on the practice exam? Let's bring up the practice exam right here. Which practice exam question? You're welcome, Matthew. Gracias. Está bien. You didn't ask who I am. I am good, though. Cassie's marked the question. Here we'll bring up MuBot to help us find review 2. Number 5, part 4. Review 2. Okay, MuBot's going to help us out right here. You're welcome. Thank you, Cassidy, for asking. And we got lots of review videos. It's really great to mention. And so do feel free to ask. I don't want to be like, oh, there's a video for that. I know I say that all the time. Well, thank you, Matthew. I know I say like, oh, there's a video. But if you ever use the video and then the video doesn't help you, that's where coming to office hours is really great. Stat 201, review test question. Which one number? Number 5, part 4. Question 5, part 4. So we'll probably go through all the parts here. Make sure to mention the things as we talk about them. And do realize we do have review videos right here, going over each one. Speed runs, highly suggest them. Review videos for the test right here. And I think they might have changed the order of some of the questions, so hopefully that's not confusing. Sometimes we add or remove stuff, but that should be pretty accurate. So let's go right here. That's the key. We don't want the key yet. We won't use the key. Question 5 or... Okay. Oh, cool. Oh, it's regression. Yay, regression. Okay. So we got a regression question. Here is the regression equation. What notation should you put under the regression to start this question out? We're going to mark our notation to begin with. So I know you've probably done a lot of this question, but we're doing it the A+ way. What should we mark right here? What is all the notation right here? So we need to mark our notation to begin with on this. We can just mark values underneath here to make sure we know the notation. All the notation to help us out, especially if we're interpreting things. Great job right there. Cassie's got a lot of the great answers. And Cassie's marking it right there. So this is the predicted. We are predicting the height in inches. We have here the intercept, which is b0. We have the coefficient of the slope, which is b1. And the x variable is that. So there's all the notation. Cassie's got the slope, the intercept, the predicted y, and the x right there. We are multiplying these together. So know that. Mary was one of the nursing students that was part of the study. Suppose Mary weighs 100 pounds. So Mary's weight, her weight is a what for this? These are the easier ones usually people get, but Mary's weight is going to be a what right here? Just in notation, one thing. If I say a person weighs this, that is a person's what right there. So that's going to be the person's what. Exactly. Weight is X. Just plug into the equation. We're literally just going to take right there the weight of 110 and plug in. And we are now solving for Mary's what. So use the words over here, which literally says right there. We are now solving for Mary's what. It says it, but just know that whenever you put things into an equation to do regression, or when you do the regression equation, you are getting a predicted height. So this is y hat. Be careful, that's not a bar. Hat means predicted, and 63.9. In this instance, p hat is from a sample. So right there, we have the predicted right there, predicted height of Mary from the regression equation. Mary is actually this tall. So, and that looks like a y right there. Mary's actual height is her what? Mary's actual height is her what? Mary's actual height is her what? Not her predicted height. Mary's actual height is what in notation? So her actual height is what? Be careful. So y hat is predicted height. Y bar is mean of height. And so it's not y bar. Y bar would be the mean of height of all people. So y bar would be the mean height of all people. And the formula sheet will help us out right here, because on the formula sheet, and let me go to the formula sheet. So it won't be y bar, because that's the mean height of all people. So y bar is the mean height. We are looking for what? Her actual height is what? We probably want to look up here. Her actual height. Great job right there. That's the residual, right? Is residual equals actual minus predicted. So if she's actually this tall, that is her value of y. Does that make sense? The value of y right here. And then I think Cassie's got the right answers right there. That's her actual. So the notation for that is y. Be careful. I know there's a lot of y on here, like y bar, y hat. This is the predicted from a regression equation. This is the actual height someone is, or actual value of the y. And then this is the mean of the y over here, if we take all the observations and average them. So y just means actual, like the observed value. And so this is her observed height, or actual height, is 65 inches tall. And then we just plug into residual equals actual minus predicted. And so with the residual, I think, great job right there, Cassidy, negative 1.1 equals 65 minus 63.9. And if you look at this, she was taller. Wait. Oh. I think oops. It should be that, right, Cassidy? Because she was taller than she was predicted to be. So if you look at the line would have predicted her to be 63.9 when she's right here, but she was taller at 65. So her residual is 1.1 because she is what? What does that concept mean right there? So the line predicted her to be 63.9. She is, yeah, exactly. And that's a good way to check it. She is whatter than what? So think about just a sentence here to practice. The practice is key to think about what the residual means. She is what? She is 1.1 inches taller than she was predicted to be. And so that's key to know about the residual right there. And a quick drawing of it shows you the line would predict her here. And we could even put the value of X to show at 110 pounds for the height, for the weight, then she would have a predicted height of 63.9. Very important. Interpret the slope of the regression equation. So the slope is going to be, for each 1 unit increase in X, we expect Y to increase by B1 on average. You will have to write this out. So we would go right here, for each 1 unit, or for each additional pound of weight, we expect someone's height to increase by, and then 0.085 on average. Great job for each one. Yep. And look, literally, we almost have the exact same thing for each additional pound of weight increase. And then we got to be careful right here. We need increase or decrease. Depends on if the slope is negative or positive. But important things right here, plug in your value of x. We expect, don't say will. I take off points if someone says it will increase, because it's not that it will do this, it's just the expected increase there. So the key thing is if you marked your notation, what can you do if you marked your notation right here? So if you know where your x is, if you know where your y is, and that's predicted y, and that's why we say expected, or we could say predict y. And if you know if it's going to be increase or decrease, so it is going to be increase because it's positive. And then the B1 is just going to be the final value right here, which is this. And if you look at what we've done, we pretty much have just plugged in all the numbers. So knowing how to do this is very important. We expect x, or we expect height. And there we go. And I usually put the context for unit for each additional pound of weight. We expect someone's height to increase by 0.085 on average. Marking the notation makes that a lot easier, and just knowing where to find those values. Okay, so last one here. John, another nursing student, was part of this study. He is, let's just click right there, is 68 inches tall. What has it given us right here? Is 68 inches tall. That is what? We should mark the notation of this problem. Is 68 inches tall. So immediately when it says is, they are this, that's the actual, right? So y equals 68. We used the above regression equation to predict his height, and then calculated the residual. What is up with the grammar? And found that the residual was negative. I hate that the negative's off the side. So what is the notation for this? And then it wants his weight. So how much does John weigh? So what is the notation for the residual it just gave us? It just gave us E equals negative 1.47. And then it says, what is X? Does that make sense? It's saying, what is his weight? So how much does he weigh, which is the value of X? Now, there is no Y bar for this one, though. There's no Y bar. Y bar is the mean of all the Y observations, so we don't have any Y bar values for this one. Good job, Jesse, right there. But this one does not include Y bar because this is all on regression. You can use Y bar sometimes in regression, but we won't use this right here. So let's go ahead and try to solve this out with what we have. Now, I want you to notice, what do you think we can get? So if we have this information right here, what could we get? And look at the equation sheet. Notice what we have, and then think about what we could solve for. We have his actual height. We have the residual. So what could we get right now? We have his actual height, and we have the residual. So what could we solve with this information currently? Not Y bar, though. Y hat. We can solve for Y hat. Good answers in the chat. So E equals Y minus Y hat. And so we're just going to plug in the values of negative 1.47 equals 68. And this would have to be positive, so it's going to be minus 69.47. Now you can work this out by plugging in the Y hat, but I was just thinking how it has to be higher because he's going to be shorter than he was predicted to be. Once again, if you want, just plug in Y hat right here. And to solve for Y hat, you would go over here and you would subtract from both sides. So you'd go minus 1.47 minus 68 equals Y hat. Does that make sense? If you just solve this out right here, you will get the value. So you just subtract from both sides the negative 68, and you will find that Y hat equals to, oh, and that's minus Y hat. So it would be minus that. Oh my gosh, I hate that it zooms out every time I do that. But that would be right there. It's minus Y hat. I forgot the minus on it. So if you're wondering, I guess I should show that. I did forget this minus right here. So it would be minus Y hat is equal to minus 69.47. So double check your math. Make sure you've got this equation working correctly, that the value there solves over there. So now that we know Y hat, what other equation do we have? Well, we can use Y hat here, right? And think about this. We know what the intercept is. We know what the slope is. This whole problem now becomes a what for what problem. So I'll start plugging it in. Now that we know what Y hat is equal to, this whole problem becomes a what for what problem. This is one of the tougher problems. So it is equal to Y hat is equal to 69.47 equals to Solve for x. So we know right here the rest of the equation, and so we're just going to subtract off from both sides. 69.47 minus 54.55, and that's that. So 14.92, and is that right? There it goes. And then equals to 0.085, and we'll just call that x for the moment. Then we're just going to divide both sides by this value right here. And there we go. So 175. Was it 53? Equals weight. What could you now do that you have this? Oops. What could you now do that you have this value of weight? Now that you have this value of weight, what could you do now that you have this? What could you do to check your work? Now that you have the value of weight, what could you do to check your work? Now that you have a value of weight right here, what could you do to check your work? To be like, is that correct? To see if that value is correct, what could you do? Because that's you say he weighs this. So what could you do to check your work? Like you're like, oh man, I just did all this work right here. Let me check it. How could you check it? Here's a hint. Plug in it. No, Cassie, great question right there. Plug in. This is a like the more you know, the more ways you can check your work, the better. Cassie, thank you for saying I don't know. That's a great thing to say. All the point buttons right there. I don't know is a great answer, but we can plug it back into the equation to check our work. We're just going to take this value, times it by this, and then we add the other value to it, and we get the value right there. Does that make sense, Cassie? Seeing this, like this is the value of x right here. And then we can plug the value of x back into the equation to see if it solves for the predicted. Then the predicted would go right here, and we would do the actual minus the predicted, and we'd get the residual, which is the information it gave to us. This is a good, tough problem. It's a lot of steps. Definitely people, I think this is one of the major ones. We'd look on the test. Maybe 20, 30% of students were getting it right. It definitely requires multiple solves. So some questions are just like, do one thing. This one requires like a whole multi-step thing, hence why it's worth 4 points. And then we'd get partial credit depending on work when we were grading this. I remember grading this question quite well. It was fun. We should go back to written tests. I kind of prefer them. Any questions on this right here? I think we have go. Let me see. I think I have a 1:30 meeting. Written tests are greater. Those are good right there. The work it was, yeah, there's a lot of ways to work this. I wonder what the key shows. Let me look at the key. Sometimes I don't like the way the key solves stuff. It's just another way to solve things. So that's why, it's good to do things right here, because there are different ways to solve these. Here it is right here. Okay, so they marked the notation, so very important. There's the y. He's actually 68 inches tall. Here's the residual. We do not know pounds, so same start to it right there. Then you get right here. Oh, so they're writing the full thing out to start and combining the equations. So they're saying here's the equation for the residuals, and then y hat is equal to this. So they've got the two equations. We're going to use these two equations. Then they're combining the two equations right here, because when you look at the end of this equation, well, there's the end of it. Y equals E equals actual minus, and then they're taking the predicted. So the predicted is this. So they're just subbing it into here. It's a decent way of solving it. So they're plugging, since this is y hat and y hat is equal to this, we're just going to do the actual minus residual equals actual minus predicted. We know what the residual is. We know what the actual is. And then now it just becomes a solve for x problem. Pretty good way of solving it out. I think hearing it all out, hearing what we're solving for is kind of better. So just working it, I just did the first equation and got what the actual was, or we were getting the predicted. So I just solved the predicted and then solved it in where they were taking and doing the notation to start. Oh, yeah. And then there's the x right there. Yeah, it can get tricky with all the notation right here. That's why I prefer to just break it down into parts. Like, what do we have? What are we solving for? And I think we are meeting at 1:30. Good with either. And so, Cassie, thank you very much right there. And then I'm trying to think. I can't remember how I solve it, but it really comes down to practice with these problems. knowing what you have, knowing what you're being asked for. So the more you work these problems, the more practice you get, the better. There's a lot of tricky problems on the test, like that if you don't know the notation, you won't be able to get the questions right. So here we'll do one more practice problem with someone. Did someone want another one? Cassie, is there another one on the practice test you're wondering about? I think we have just enough time to do that because I have a 1:30 meeting today. Do you have another practice problem from the exam that you'd like more info on? Just say number this and we'll do another practice problem in the exam. Do remember, and once again, I'm not saying this because I'm like, oh, just go watch the videos, but do remember there are videos. They usually load in. Yeah, go ahead. We just have just enough time right here. I've got another 11 minutes before my meeting. Number 6. Yeah, thank you very much, Mackenzie. Definitely. So let's go talk about number 6 a little bit more in depth. And this one right here. Okay, cool. Okay. A high school student is interested in attending, and this is great. People asked about probability at the start. So this is a really good probability one, and I might even solve this a little bit better these days than I originally solved. We'll try to do number 10 too. We might have just enough time. We'll try. Okay. So 118.33, stat 1, review test question 6. Okay. So here we go with this question. No worries, Mackenzie. Let's do it. Thank you so much for your questions. So what do we have right here? This is a lot of info to just tell you what. A lot of info for this question just to tell you what. And then we should look at how many schools are they applying to? 8. So what do we have right here? Yeah, we'll try to do number 10 too. This one, if we know how to do it, we can do it pretty quickly, but it's a tough one with 5 points. What does this mean? And what does this mean? That's all the important things for this problem, which you could create many problems from. And then accepted to at least 1. This is all the info we need to understand this problem. So 38%. Yes. So we have here the probability. So we're talking about they're trying to apply to 8 schools, and they have a probability of accepted of 38%. Okay. So what would be the worst thing to occur? I usually write probability accepted. It can be kind of known as P, but I usually put P with A in parentheses for probability accepted is 38%. That's the way I best, because it's not quite P like proportion, but it is a probability. So it is kind of like the Mackenzie 100 points. I like to put PA right there for like probability of what we're talking about. And then the probability of not accepted, which either they're accepted or not accepted. And you could say, well, what if they're waitlisted? Well, that's not quite accepted. You're either accepted or not accepted to the school. Not accepted could mean waitlisted or deferred or whatever they do these days. So with this right here, what are the 2 things that could occur? Write your sentence. So let's write out 2 sentences of what could occur. I need 2 sentences of what could occur. And one of them should be related to this. That's one of your 2 parts of the sentence. You need this or this. And it's everything that could occur. You either get rejected from all or accepted to at least 1. Exactly. So you're either going to get rejected from all or accepted to at least 1. There's nothing outside of this that could occur. You say, what if I'm accepted to all of them? Accepted to all of them would mean you were accepted to at least 1. So now that we have this, we know that one of these things must occur, and the or becomes addition. Do realize you have a lot of hints on your formula sheet. Let's go look at the formula sheet again. So many hints on the formula sheet, which you can print off or write down, make sure nothing else is written on it. But the formula sheet right here does talk about the addition rule, talks about complements, and you can see right here, these are mutually exclusive because you can't get rejected from all and accepted to at least 1. One of those things would occur or not occur. So now it's going to be harder to find this, but easier to find rejected from all. So the probability of getting rejected from 1, and this is just 1, so that would be not accepted. We'll call it not accepted. The probability of, or we'll say probability of rejected, because we did put that down there, is 62%. So what is the probability you get rejected from the first, and rejected from the second, and rejected from the third? What is the probability of getting rejected from all of them? 0.62. And then what do we do with that? Jesse's on track with it right here. So what do we do with the 0.62 because you get rejected from the first, and rejected from the second, and rejected from the third? And this eventually becomes the mathematics of 0.62 raised to the 8th power because it's happening 8 times in a row. Great job, Derek, following along too. So now we simply have the following right here. And guess what? We just algebra it over. So now that we have this written out, we can algebra it. And the answer is going to be as simple as solving the equation. So 0.62, 2, 3, 4, 5, 6, 7, 8, 1 minus, and there we go right there, 97.8% probability. So it seems very likely they will get accepted to at least one. What's really neat, I did mention the binomial applets earlier on in this video, but it can actually be solved with the binomial applet. So if we went over here to binomial, you can actually really quickly solve a lot of these questions. Was it 32%? And you could find the probability of, wait, I must have the probability wrong. What was it? It was 38%. There we go. So the probability of getting rejected from all of them is that. And that's literally what we found right there on the calculator. If I put this right here and hover over it, well, I got to put it down here then. There's the probability of, and you can then even use this to solve. Go right here and say the probability of greater than or 1 is that right there. And there's the probability. And yeah. So, but once again, we are trying to explain how to do these things. We're trying to understand the concepts behind them. There's many ways to solve these problems, but understanding what we're talking about when it comes to probabilities, being able to work through a problem and explain to somebody that you're either going to get rejected by all of them or accepted to at least one. And then this here shows it conceptually that you will either be rejected from all of them or accepted to at least one. There's many ways to get accepted to at least one. It's super unlikely you would be accepted to all of them. Accepted to all of them is 0.62, 2, 3, 4, 5, 6, 7, 8. Or wait a minute. Rejected from all of them. Probability accept. Oh, that's accepted to all of them. Oh my gosh. So the probability accepted to all of them, 2, 3, 4, 5, 6, 7, 8. And we'd have to really zoom in on this to get that probability, I think. We got to zoom in. I don't even know if we can get it. See, that's where the applet fails you and you can't get the answer. But that probability over there is that right there. Very, very unlikely to get accepted to all the Ivy League schools with a 38% probability of getting accepted. And I think my meeting starts in 4 minutes. Here, let's do a speed run of that question, Cassidy. You ready? You said number 10. Let's do a speed run of said question. Number 10. Here we go right here. Ooh, can we do it? Oh, this is margin of error. It shouldn't be. This shouldn't exist. This is not on the test. It's margin of error. It is on test 3. Cassidy, 100 points for mentioning this. So calculate the margin of error. Here, take a look at this, Cassidy. You ready? The margin of error of something, like if I tell you, I don't know why we haven't removed this. It should be removed. If I tell you dinner at a fancy restaurant is going to be between $30 to $50, how much would you estimate? This is test 3. Yeah, we should mention this. I need to call it out. It's not on the test. It shouldn't exist. If I said to you dinner costs between $30 to $50, how much would you estimate dinner to be? How much would you estimate dinner to be? It's going to be between $30 to $50. Well, 30 to 50, but how much would you estimate it to be? What do you think it would be? What's a good guess of how much dinner would be? If I say it's between $30 to $50, you would guess it would be between about what? 40. So it's 40 plus or minus what? What is the margin of error on this? And then you'll see the margin of error is just half the length of the interval. There's the margin of error. Boom. So all you have to do is take half the length of that interval. It's just not nice numbers. So the length of an interval is how far are the numbers away. This is on test 3. And there it is right there. That's half the length of the interval. Yep. It's just how long is the interval divided by half the length. So the same concept applies with numbers that are not as pretty as 50 and 30. You just take the length of the interval divided by 2. The two ways they could make the interval smaller, make the margin of error smaller. So margin of error is y bar plus or minus the t-score. Or we're doing t. Yeah. No, we're doing proportions for this. Oh, I got to leave in 2 minutes tops. So it's, why is this on the practice test? P hat plus or minus Z star P hat. So the two things we have control over right now are the sample size and the confidence level. So the two things they could change, we can't really change what we see. Like we can't change the observed sample proportion or the complement. We can just change our confidence level and we could change our sample size. So if we want a smaller margin of error, we could increase the sample size. So the sample size could be larger. That would make this equation smaller, or we could go to lower confidence. You're welcome, Rachel, right there. This is not on the test, not on the test. Got a meeting coming up right here. We will be reviewing for both classes, and both classes have the links to both videos. Bye for now, everybody. Outro screen.